Welcome back to Unit 9. This is the second lecture, and in this lecture we will be talking about the conservation of momentum, and just like the last lecture, we only mean translational momentum still.
Hit me with your best shot! Come on, hit me with your best shot! Hit me with your best shot! Fire away!
Whoa, what's going on in that situation? Well, it turns out that the reason that guns recoil or move backwards when you shoot them is because of the conservation of momentum. So let's talk about that idea for a second, the conservation of momentum. Well, momentum we've already defined, but just like energy, it's not always conserved. So when is it conserved? Only if you are in an isolated system. So what is an isolated system? That would mean that the only forces that are acting on the system that are unbalanced, the only unbalanced forces, are between the objects in the system. Or an equivalent way to say that would be there are no external net forces. The external net force must be zero in order to have an isolated system. So if you meet those conditions, congratulations, you have an isolated system and your momentum is conserved. We also have to make special note of the vector nature of momentum once again, just like the last video. It has to be applied separately in each dimension. So sort of like when you do a force diagram, the forces in the x dimension are different from the forces in the y dimension because they're independent of each other. Same thing for any vector. You have to treat each dimension like its own separate problem.
No, 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 no. ¿Qué? No, ¿eh?
So was the momentum conserved in that situation? I guess it would depend on what you define as your system. So was the momentum of the cup, only the cup and nothing else, was its momentum conserved? Absolutely not. And let's think about why. So the momentum is mass times velocity, right? Well, the cup started at rest, which means its velocity was zero, and therefore its momentum was also zero. And then the kitty laid paws on it and moved it, giving it velocity. Once it had velocity, it had a momentum that was non-zero, therefore it had changed. The unbalanced net force on the cup from the cat means the momentum changed. Let's try another example. Suppose you have two ice skaters on a icy, frozen, icy pond. You remember those physics code words, icy, frozen, all those? Those mean frictionless, so we have no external frictional force on these skaters. They begin at rest. They're sitting here, motionless, touching hands, kind of weirdly, but whatever. They're going to push off of each other, and after they do so, we want to see what happens to them. Will they move backwards, and if so, will they move at the same speed? Let's find out. Whoa, did you see that? Maybe we should watch it again. As you probably saw, as I hope you saw, the skater that was more heavy, which was the skater on the right, the 100 kilograms, he moved much faster than she did because they exerted the same force on each other, but that means that because of the difference in mass, they have different accelerations, and therefore after they release, they're going to have different velocities. One will have accelerated more than the other. So let's look at this from each skater's perspective. If you're the 50 kilogram skater, the one on the left there, was your momentum conserved from before the push until after? Well, seems like no, right? I mean, you were at rest and then you were moving, so your momentum clearly changed, and that is correct. You have no conservation, or you do have a change in momentum. What about the 100 kilogram skater? Well, same story, he was at rest as well, and then later he was moving, so his momentum changed. But what about the two skater system? Well, if we define our system to include both skaters, that means that the only external net forces on the skaters are from each other, which we would define as an internal force, or objects in the system exerting forces on each other. Now, there are still forces from gravity and from the normal force of the ice, but those are balanced, and therefore their net force is zero. So without an external net force, yes. Yes, the momentum is conserved for the two-skater system. Let's look at that example again. We're going to try this mathematically now. We're going to start with a momentum of 0. Each skater is motionless, and therefore its velocity is 0, and therefore both momenta are 0. Well, if I have a total momentum of 0 combined, that means after the push, we should still have a total momentum of 0 because they're an isolated system, and therefore there is no change in momentum. It is conserved. Now here they are, some distance apart after they've pushed off from each other. We're going to give them velocities here, 2 meters per second to the right for the 100 kilogram skater, and 4 meters per second to the left, and the vector nature of velocity is designated here by the direction of the arrows. But remember what we talked about in the first video. This is really a -4 because without the arrow, we use signs to designate direction. So what's going on with the total momentum of the system at this point? Well, we could define that, change it to a -4 here, by finding their total momenta separately and then adding them. Well, this guy's moving to the right. 2 meters per second is his velocity, 100 kilograms, that's his mass, and therefore his total momentum after the push is 200 kilogram meters per second to the right, or we'll call that positive. To the left, well, she has a mass of 50 kilograms, that's the subscript here, and a velocity of -4 because her direction is what we've defined as negative, and therefore her momentum is negative 200 kilogram meters per second. What do you get when you sum those? 0.
Oh, I believe I've just shot John.
Excellent shot, sir!
Which is why that doesn't make a whole lot of sense. Is that there's enough force in the bullet that it should knock this guy completely off his feet. Let's watch that again. Then there's enough force pushing backwards on the gun that it should knock the shooter off his feet. Hollywood has no concern for the laws of motion. This is, I just found this and I think it's funny, but imagine what happens here. It's not only Newton's third law. The law of conservation of momentum is Newton's third law. It's the same thing. But since we assume that the surface of the water is essentially frictionless, what happens if this guy starts shooting this machine gun forwards? Well, he's going to be propelled backwards, slower because he has more mass than the bullets, but still because they exert equal and opposite force, he will accelerate in the negative direction. Here's a great example. I got this from the webcomic XKCD, and if you don't read that, I strongly recommend that you start. It's fantastic. There was a reader who submitted a question to this webcomic and asked if it would be possible to make a jetpack out of guns. And as absurd as that might sound, it turns out it's actually possible. Here's how it basically works. The Saturn V rocket works by expelling jet fuel at a really fast rate downwards, and because of conservation of momentum and Newton's third law, it pushes the mass of the rocket upwards at the same time. The same idea would happen to a gun if it was fired vertically downwards. The bullet would be projected downwards, and then the gun would be projected upwards, albeit with a much slower velocity, but enough to lift it off the ground. Turns out that one gun is enough to lift a squirrel. That's about all. But if you wanted to make a jetpack, or basically a jetpack for a person, you could just use a whole lot of guns. And if you did that, and don't try this at home, you could actually accelerate upwards at a very quick rate. What I want to talk about is whether or not we can make an isolated system out of this, right? So remember that an isolated system is one in which the only forces present are between the objects in the system, or more accurately, the only non-zero net forces present. Because you can have balanced forces from other things, they just wouldn't make a difference. So let's find an isolated system. How about you, assuming that this is you up here on the platform? Will your momentum be conserved? No. In other words, your system is not isolated. And the reason is that you will be accelerating due to the force of the platform pushing on your feet. What if we include the platform? Well, that would still not be an isolated system because the platform is being pushed up by these guns down here. What if we include the guns? Then we have an isolated system? No, unfortunately, the guns are being projected upwards by the bullets. So what if we put the bullets in the system? Would we then have an isolated system? Still no, because in the entire system, all four things we've included so far, we have a non-zero external net force due to gravity. Since that comes from the entire Earth, we could then put that in the system, and you would have an isolated system. So it's always possible. You can always find an isolated system. It's just sometimes absurd how far you have to go to do it, and it's usually easier to analyze these sort of things using Newton's second law, which states that the acceleration of something is given by proportional to the net force acting on it.